I guess. And he's going to talk about both NGC 6537, which was his original plan, and NGC 2440. And I just want to say that I think it's interesting that NGC 6537 is what I would call a first cousin, or maybe near sibling of the Butterfly Nebula. And
Twin.
okay, that's close.
Go ahead.
And then 2440 is maybe a cousin. All three of them come from higher mass progenitors, intermediate mass stars, and are nitrogen rich. So that's just an interesting fact.
Thank you, Harry. Yes.
Take it away.
Okay. Oh, I'm gonna use this. Okay. Thank you. Yes, obviously I'm not Paula Moraga Bez, and I'm going to do my best to merge her talk with mine. Fortunately, we're talking about the same data here. So Paula has just taken on a job with the burgeoning Western Ontario group as a postdoc, I'm pleased to say. Thank you, Jan. Thank you, Els. And she would have presented this herself, but couldn't make the trip here this time. Let me make sure I can advance things properly. So this was the...
A little louder, please.
Yeah, that was just an aside to myself, if I can handle the electronics here. Okay, good. All right, so we've assembled a short list of objects that Harriet was just referring to. These are bipolar planetary nebulae, molecule rich, high excitation, temperatures exceeding 150,000 degrees, central star temperatures, that is. In nearly, I think, in all these cases. And we've been attacking them in various ways. I'm not saying this is an exhaustive list of the objects. One thing I should have mentioned, these are all detected in CO, quite bright sub-millimeter CO lines, and near infrared molecular hydrogen, which is how I got to know and love them from a survey we did about more than 30 years ago now, an imaging survey of molecular hydrogen and near infrared. Let's see, NGC 7027, we have a NOAEMA survey, as I mentioned. NGC 6537 was covered in an ALMA archival program, and the rest of them we observed in our own ALMA program, and I'll discuss that a little bit more. And this was the subject of Paula's thesis, by and large. And you can see some dynamical ages laid out here. I'm not going to go through all of them. You can read them yourselves, but it sort of very suggestive of an evolutionary sequence. And these are questions that we want to ask about these objects. What are their intrinsic structures? What's the origin of the molecular gas and dust? How does it survive and evolve? Is this an evolutionary sequence, or are we just fooling ourselves? And are all these objects, as Harry just mentioned, are they all descended from relatively massive progenitors? So yeah, let me make sure I can advance here. Okay, so yes. So I'm picking out these two, as you know, NGC 2440 and NGC 6537 for this merged talk that Paula and I are giving, as it were. And here's some basic information about those objects. Distances, central star temperatures, and so on. You can read them for yourselves, but these are, again, nearby objects. That's why we picked them. We tried to pick objects that were within a couple kiloparsecs so we could resolve them very well, and they had been well studied. I should mention that, hundreds of SIMBAD references for each of these objects. Let's see what else to say about them. Very large luminosities. In the case of 2440, the initial mass is probably known pretty well. I would say in the case of NGC 6537, we don't know the initial mass all that well, but it should, as we were just mentioning before, it certainly does resemble NGC 6302, our poster child for this conference in many respects. Sorry, this is a bit of an eye chart. I have a couple of these in the talk, and I will run through them, and we can go back to them if you would like me to. But this is sort of the summary of the observations I'm going to talk about in the next 15 minutes or so. We have a joint Chandra JWST program that has now been fully carried out. A little aside here, if you want to get JWST time, sometimes it's a good idea to go through another observatory to get it, because I had tried and failed every single cycle to get the objects that you just saw in the previous slide as a group. So we picked them off one at a time using this joint Chandra JWST program. And anyway, we wanted to find out if these are X-ray emitting objects for various reasons I'll mention. JWST, we used NIRCam, we used these filters that isolate iron 2, molecular hydrogen, PAH plus continuum, and bracket alpha. This is an interesting set, as you'll see in a second. The Chandra imaging, we got 80 kiloseconds of Chandra HRC imaging per planetary nebula. We had to go the route of the HRC instead of ACIS because ACIS now lacks the soft sensitivity. And here's a spoiler alert. We did not detect either of these objects. I was not particularly surprised based on the results of the Champlan survey, but it still gives us some interesting information that we can use to understand these objects. And then with ALMA, I mentioned these molecular line surveys we've carried out. For these two objects, the sources of the data are different. Caroline Gieser was the lead on a survey of compact H2 regions, and this object, fortunately for us planetary nebula fans, was included by mistake in their list of compact H2 regions. Caroline's been an excellent collaborator on this project. NGC 2440, this was part of our more extensive survey, the one that Paula investigated for her thesis. So here is actually a capsule summary of the results of Paula's thesis, but it's just a tiny chunk of the thesis work that she did. And this is showing the HST images in most cases, H alpha, it's not HST images in all cases, H alpha and nitrogen 2, and the red and contours is the CO distribution. So in every single case, we detect what appears to be a molecular torus. Not particularly surprising, but the details are very interesting in each of these objects. We can discuss that further if you like. Here is NGC 2440, which is the subject of this particular talk. And here's the channel apps. You can see some very interesting kinematic structure here. And if you look at the moment zero image and the spectrum, you can see that what we are seeing appears to be a toroidal structure with some flowouts. And that's the way that we've interpreted, Paula has interpreted those data. And that's kind of interesting in various respects that I hope I can get back to. This is the line survey. I'm not really going to talk about these data other than to say there's a nice chemical mixture here. It's very interesting in terms of the implications for ultraviolet and X-ray, soft X-ray irradiation of the gas. And in every single case, it's this sort of toroidal region in the center that seems to show up as the brightest emission. So here is the HST imaging that has become rather famous now. Well, we've picked 2 images. We've been trying to get wide field camera 3 images of this object forever. I'm going to just keep trying until one or both of us, HST or me, dies. Here is the big reveal, I suppose. The JWST NIRCam imaging of 2440. In bracket alpha, well, okay, it looks a lot like the H alpha image. You go to iron 2 and you start to see the nice smooth emission you see in bracket alpha kind of breaking up into distinct regions of excitation. In molecular hydrogen, it's a totally different beast, which, when I saw this image, obviously my jaw hit the floor. We'd sort of seen hints of this from ground-based imaging, but we had not seen such an amazing, I think, complete outer shell, especially. I'll try to mention that in a second. And then the PAH imaging looks a bit like the molecular hydrogen. Overall, the emission morphology is similar, but other parts of the nebula are lighting up in different ways. So it's handy. Let's see. I'm sorry. This is a blow up of the inside portions, the core region of the nebula. What a mess is all I can say. And it's an interesting mess for all kinds of reasons. It looks like we're seeing various different directions of outflow. In particular, there's this larger structure that's sort of cutting through at 45 degrees, and a structure that's more or less headed east-west. And those two correspond to the main bipolar lobe sets that have been known from HST imaging and from a very nice treatment of the kinematics of this object by Lago and Costa, I believe, about 10 years ago. So from this overlay, you can see that we're seeing nested structure. We see the molecular hydrogen lining the outside of the nebula in this what appears to be a sort of quasi-spheroidal distribution. And you see in interior of that the two major lobes that you also see in the HS and the HST image, and then you see this second bipolar nebula that's superimposed on that object, the larger object. Let me just see if we can go back and forth here. Yeah, okay. So I like to just kind of click back and forth between these two images. The only difference between them is which we've put into the blue channel. And here you see the iron 2, which appears to be mostly lining the larger lobes. Although if you look carefully, you can see that it's also lining the smaller bipolar that sits within those lobes, or the more narrow bipolar nebula. So let's see. Zooming in, we can now compare the hot shock, very likely shock excited, maybe partially UV excited, especially in the middle, molecular hydrogen emission, and we can compare that to the ALMA distribution. You can see that they look quite similar in terms of the brightest filamentary features that you see, and you especially see that torus outline fairly nicely. And we also see in the ACA data that we have, the lower resolution, wider field data, we see these molecular bullets far in the far exterior of the second bipolar nebula that's imposed on the first bipolar nebula, if you like. Those bullets were known before from single dish CO mapping. We're detecting them not just in CO, but in CN, HCO plus quite brightly, HCN not quite so brightly. This is probably shock excited HCO plus in those bullets. And the dynamical ages of these two flows appear to be quite similar, although the core, it looks like maybe was slightly preceding the bipolar flow that's generated those bullets. I don't know if I put, at this point, the analysis that Paula and I have been able to do, I don't know if I put a lot of stock in the difference between the dynamical ages here, but there's some evidence that perhaps the torus ejection preceded the outflow that generated those two bullets. So let's see, this is again an eye chart. I apologize, it's sort of just highlighting the major takeaways here. We see a quasi-spherical HEV outflow with two distinct misaligned embedded bipolar nebulae. The flow dynamical ages are something like 1,000 years. We're seeing the cold and chemically complex toroidal region with some blowouts. It has a dynamical age of something like 1,200 years in the ALMA data. Perhaps this is showing us the jet lag that Pat Huggins documented about 15 years ago as a potential characteristic of bipolar nebulae. Jet lag being the lag between the time that the torus is ejected, followed by the ejection of collimated flows, jets. The PAH emission matches the H2 quite nicely overall. The iron, however, appears to be more widespread within these polar bubbles, and that does appear to be an ongoing set of shocks. Really, just 4 minutes left of the 20. Oh man, okay, all right. Well, I didn't want to blat for more than 20 minutes anyway. So, okay, let me move on to NGC 6537. We can go back to any of these you have questions about. This is a paper that just came out. As many of you know, I wasted a lot of grant money. I mean, I spent a lot of grant money buying people drinks the other night because this paper was recently accepted. Just quick summary of NGC 6537. The low kinematics are very well established. It's got flows of 300 to 400 kilometers per second, inclined by about 40 degrees or so out of the plane of the sky. Here's the JWST imaging. In molecular hydrogen in particular, I'll point that out first. You see the complete bubbles, which had not been directly detected before. They appear to be nearly complete, probably perforated bipolar bubbles. Iron 2, an S shape. Also not surprising, we know from 6302 we often see this, and in fact there it is again, or I should say we saw it in one case. That's NGC 6302. Maybe we're often going to see this. Is a better way to put that. We detect the central star quite brightly in the longer wavelength images. Here's the molecular hydrogen image of black and white scale. But we now know the polar lobes extend to about a parsec. So the dynamical age of the lobes is something like 3,000 years. Zooming in is an overlay of the iron 2 on top of the molecular hydrogen. Looks a lot like our friend NGC 6302, where the iron is just tracing these surfaces within the bubbles. Zooming into the core region, we see very complex structures, loops, bubbles, maybe a distorted spiral in the center. These are seen in continuum because they're all showing up in all of the filters, the emissions showing up in all the filters. And there's this appears to be a pH bright bubble surrounding the central object. This is the same series over here. These are pure. This is the pure ionized emission, if you like, the H alpha bracket alpha and ALMA continuum at 3 millimeters, and they show this kind of layered structure. We interpret the H alpha bright features as the ones that are in the lobes coming toward us, and the ones that are seen more brightly in bracket alpha are moving away from us, and then in the center you see sort of a pancake structure, the ALMA continuum, and that's the equatorial plane. That's the center of the torus, the ionized torus. We also see the torus in the ALMA images. When I first saw this, I was quite puzzled. Why is the blue shifted emission sitting on top of the rearward facing lobe? Well, it's because it's 90 degrees orientation from the lobes, and that's actually the torus. So that material is the expanding torus coming toward us to the north and moving away from us to the south. So the torus is perpendicular to the lobes and with a distinct twist. Its dynamic age is more like 8,000 years, considerably older than lobes. So this is our cartoon analysis, quote unquote, of this object. Just very similar to NGC 6302 in so many different ways. Here's a comparison with some models that Bruce ran. I said, Bruce, do you have any models that might look like this? And he immediately sent me this. And you can see that we're seeing many of the same structures that you would expect if you get a bipolar flow impinging on a pre-existing AGB envelope. There are lots of caveats here. You can read the paper and understand that we're not as confident as it might appears to be in this comparison. It's just a representative model, but it does a pretty good job. I especially like the fact that the region that's lit up in iron 2 is indeed supposed to be a hotter region where the winds are interacting most strongly. One more thing, very important, the central star has a near infrared excess. And so we're seeing very likely a disk around the central star, perhaps a circumbinary disk. This keeps popping up in HST images of bipolar nebulae. Albert and Orsola and I have scratched our heads about this for quite a while now. Circumbinary disk, maybe so. Okay, so conclusions, you can read the paper. And it's very bad. This is bad form. Junior researchers never quote yourself on a slide that you're showing in a talk. But I'm just going to leave this up here. No, I'm not going to leave this up here. I'm going to leave this up here. There. Okay. Sorry for going over here.
I think we're a very exciting talk. So we only have a couple of minutes for questions right now because of our time pressure. Are there a couple of previous slides?
I put the previous slide just.
Maybe. Let's see. What's back? Yeah, back. This. Yeah. Oh, you want to read the quote? That's a waste of your time, you know. You can read the paper. And by the way, this is nothing that anyone in this room would probably argue with. It's rather generic language, and this is okay. It's maybe a little intentional. I'd like this paper to be read by something other than by people other than that are those in this room, because I think it's just an interesting lesson in the different components that you can get from a single binary system, perhaps in a nebula.
Well, I have a question, but I'll save it for the discussion. So there
I
are
didn't even ask a question. I was answering something.
Yeah.
Yes, I'm sorry.
Is it my turn?
Yes.
Okay, thank you. Thank you for sharing this message. If you really want to make us theorists suicidal, you know, this is the way to do it.
Please.
There's one small remark on that S-shaped stuff, right? In the hydro simulations I did a number of years back, it turned out that you can actually reproduce that quite simply if the constraining disk is not flat but is warped. Okay. And I think that you do see that signature here as well.
Yes, this is a very warped disc. I would agree with you in many, many different respects. Yes.
One more. One more question?
Yes, thank you. It's great data. My question is, in case of the iron two, if you have taken into account the hydrogen line that is 0. It's a hydrogen line that maybe looking at two data, this object probably is not more likely, but the other one, bracket alpha and iron, so quite similar. So it should check. Compute theoretically the line and then subtract to see if there are remnants.
Thanks you. Thanks, Starbucks. Fair enough. Yeah, the narrowband filters on JWST have no offline component complement. So we're
Okay.
unable to do anything about the continuum subtraction or anything like that, or lines off band. Good idea. Yeah, thank you.
Okay, well, we'll move on to our last. Our last standard talk late speaker. So we are going to hear from Miguel Santander Garcia, Shaping the Ring Nebula. You're gonna hear about another iconic nebula.
Okay. Good morning, and thanks to the organizers for the opportunity to present this work. Well, I don't need to remind you of the problem of the orientation of planetary nebula. In this regard, morphokinematical modeling can help getting a picture of the three-dimensional geometry and velocity field of this nebula, and also the spatial orientation as well. Now, morphokinematical modeling, again, plainly as that, it's just purely high school physics, right? But it can be enhanced with radiative transfer, at least in molecular species. You can use shape mole along shape to initially to work with CO species at the beginning, and that allows you to go beyond normal morphokinematical modeling, compute masses and physicochemical conditions for gas, and so on. As I say in the beginning, we could use only CO species in shape, but now thanks to the work by Elisa Massa, we have a whole new bunch of molecules you can work with. You can see a practical case of this in Elisa's talk in next session. Now, I'm going to talk about the Ring Nebula. The nebula is very large in terms of its apparent size in the sky. It's more than 1.5 minutes across, plus a halo with 3 minutes or so. And its shape, well, it's clear. It's a ring, right? It's in the name. So thank you all for your attention. The problem solved. Now, really, the shape has been debated for many decades. In fact, as Romano Corradi, my PhD supervisor, once put it, 2 astronomers, 3 models. There are many models. They fall into 2 broad categories. First, we have this model on the left, which is basically an ellipsoid seen almost pole on, with a halo around. There's another one category, which is a torus, and then a biconical outflow, quite inclined to the line of sight, like 30 degrees or so. And also there in the submillimeter, there are models in CO like that from Rafael Bachiller in the late 80s, who modeled it as a cylinder quite inclined to the line of sight. Now, quite recently, last year, Roger Wilson and collaborator published this paper with a view of the JWST, where you can see, first you can see arcs, beautiful signature of arcs probably from a previous spiral win by an AGV with a companion, with a white companion. And they interpreted the data as a torus, a ring, a torus with a biconical outflow. And there's also there are some clamps in here in molecular hydrogen, which are supposed to be in the far away from the star in the outflows, in the conical outflows. Now, earlier this year, Joel Kastner and collaborators published this paper with the first interferometric observations of the Ring Nebula with SMA, and where, well, you can see here the nebula is clearly an ellipse there. So they modeled it as an ellipsoid, a triaxial ellipsoid with 3 different axes. That means there's no axial symmetry. And it's oriented pole on, almost pole on, and it's hollowed by a bipolar outflow, but previous bipolar. Now, our take was, the point of the talk is that if we combine morphokinematical modeling in 2 different regimes, we can combine, well, we can maybe get a clearer picture if you combine the morphokinematical modeling in the optical, which probes the ionized region, and in the submillimeter, which probes the colder molecular region. And then maybe you can get, well, another picture, another opinion and a half. Now, this part of the work, we made like 2 different models, and one in the optical, one in the submillimeter. The one in the optical was led by Edgar Santamaria, and well, the nebula was observed along 10 different slits with the San Pedro Marti 2.1 meter telescope, with the Manchester SL spectrograph, and you can see here the position velocity plots. Here, this is position along the slit, and here radial velocity, and here you have the model. Now, with different components in different colors. Now, remember these clamps that, by the way, they are also seen in the SMA observations that are around here. They correspond to these like tiny blobs there that are in blue in there. So those clamps seem to be really in the inner ionized bubble. This is some render of the models. The model is an ellipsoid, which is inclined. It's almost in the plane of the sky, okay? And the inner bubble in blue, the clamps in red, and the outer halo in red, and those you can see there, the observed images and the synthetic ones. The ellipsoid is expanding very fast. Its velocity follows a linear velocity law, homologous expansion with up to 85 kilometers per second. Okay, you have the model again. And now in the submillimeter, we went in April, late April this year, we went to the Iran 30-meter telescope to observe, to do a deep on-the-fly mapping, scanning the whole nebula. I think it was like 4 arc minutes across. And well, we did that shortly after Joel's paper was published. So this is me right after knowing that at the telescope. Now, when we computed the integrated flux, we realized that we compared it to the recovered flux by the SMA observations. Then we realized that almost half of the flux is lost because of interferometric filtering. And then, well, this is me after realizing that maybe after all we could do something useful with the data. In that sense, merging the observations, using our observations as 0 spacings for the interferometric ones would be a really good idea. So Joel, let's talk after the talk. Okay. Now, this is the map, the 12-0-2-1 map, the velocity channel map. And there you have the integrated intensity. Now, here, well, you can see that the shape here looks a bit different than in here, in this. See, here you have like the outer envelope of the thing. And in here, what I more or less see here is like different segments of rings in different channels that they are increasing radius, so as up to the systemic velocity, and then decreasing again. So, well, this is a reconstruction, a visualization rather, of the nebula made by Edgar Santamaria, and it's quite beautiful. But there's a disclaimer here, because this reconstruction assumes some things. For starters, you have to assume a velocity law to convert from the radial velocity that you have in the third axis to the z direction. And also, you are assuming only a single kinematical age for the whole nebula. If you have two components with different ages, then you are missing the picture. And also, well, here the age you assume will get this reconstruction more or less stretched along the z axis. In this one, it's not the current model we have. This has a shorter age, so don't take that as the real structure. Now, when I modeled this in CO, I started with, well, I thought of using a triaxial ellipsoid, but I like my nebula to be axially symmetric, or at least point symmetric, for reasons similar to those behind norm selection of mate. So I modeled it as a barrel seen pole on, hollow barrel, and this fits nicely. This is almost on the plane of the sky. This fits nicely these circular rings that we saw in the map, but not the other things that the most intense, the bright blocks to the left and to the right, which instead you need something else for that. By the way, this in here in the lower right, you have the field of view in the nebula as you see it in the plane of the sky. Okay, and this is the side view, so the observer here is on the left. Okay, now if we load the optical model in shape, this is the optical model except for the halo and clamps. This is the ellipsoid and the inner bubble. And if I make an ellipsoid which runs right beyond this one, like this, in red, this together with the barrel, this part is hollowed out, so no, there's no emission there in CO. But the barrel with this ellipsoid, which runs almost perpendicular to the barrel, provides a nice fit to the overall geometry of the ring nebula. So the story would be as follows. Once upon a time, there was of course, this is a very speculative story. It's a work of fiction, so don't believe a single word. But well, we have an AGV with a white companion, and together they make a spiral. They deploy the AGV wind, and then as the AGV transitions to planetary nebula, the winds sweep up the rest of the wind, and they propagate more easily along the poles, which are more or less aligned with the line of sight. So in here, it will be something similar to this. So then this would be the barrel. And then this was like 6,000 years ago or so, the barrel. And now something like 1,600 years ago, there's another outflow which goes almost perpendicular to that, and which blows inside the barrel, distorting the walls of the barrel that we see in CO, where there's the bulk of the mass of this nebula, and then to the present situation, giving this barrel some ears. Okay, so my 1.5 opinion is here. I think if you combine these morphokinematical modelings in different regimes, you can get some interesting results. And well, in this case, we have we think we have a 6,000 years old barrel with a younger outflow which runs almost perpendicular to that. I don't think processing jets can get that wild or even warp disks, but I don't think so. My guess would be that maybe we have a triple system here. A wide binary in the plane of the sky, and then another one almost perpendicular. And finally, a word of caution: kinematical ages. the kinematical age depends on which component you measure. If you measure the kinematical age of the optical ellipsoid, it's 1,600 years. If you measure it in the years, the total component in CO, then you measure a larger age because the velocity is not that high. I think the outflow is distorting the walls, but the material beyond is still not that quick or fast. Okay, so that's it. Thank you very much. Oh, sorry.
So that was perfect timing. Okay, questions?
Here. Okay.
Thank you, Miguel, and I totally agree that we need to talk, obviously, we've talked about this before. Yes, I think combining the two data sets will be really great. You get 6,000 years, which I think is what we said in our paper, so I'm relieved to see that. And so what are the, can you just go back to what the basis is for the younger components?
What's there? What there?
The younger components, this 1,600 years and 4,000 years, what would they correspond to?
I don't know what you are referring
At the
to.
very end of your talk in the summary, you said, it's.
Yes, 6,000 years the barrel.
1,600 years and 4,000 years.
Yes.
Is that for the optical components or for the
No.
PO as well?
No, it's for if you compute the age from this ellipsoid in the optical, you get 1,600 years because it's up to 85 kilometers per second. But this component is not that fast. It's like 40 something kilometers per second. It's faster than the barrel, but it's not that fast. So if you compute the age there, you get 4,000 years around that.
And that component is from the optical data, or is it from the CO?
This one is from the optical data, and this one is the CO. And then you need to go beyond the optical, otherwise this doesn't fall there. You would get inside.
Yeah, so it's fascinating that you get the second flow in CO as well.
Yes, yes.
Thank you.
So we have the poster speakers start coming up and lining up. Another question on the other side there. Yeah.
Well, as you all well know, the AGB stars don't jump into the planetary nebula phase without going through the pre-planetary nebula phase. So would you care to comment as to what you think might have happened during the pre-planetary nebula phase of this object, which might relate to the structures that you see?
Well, I don't really know. With the data we have, it's very difficult to do that interpretation. I guess, well, if you have a wide binary AGB, you are deploying the wind and then make spirals and arcs, and then you well, I guess it will be bipolar and along the line of sight, more or less. But other than that, I can't comment at this point, I think.
You mentioned 3 stars, but you already know that there's a distant companion from Roger Russell's paper based on Gaia parallax and proper motions. So we know that there's a distant, very distant companion. And the central star is more likely the binary from indirect observations.
So-
The contact cloud dust.
So then this binary, but the orbit would be like almost perpendicular to the plane of the sky of this binary.
No, but we don't know what the orbit of the very distant.
I know the very distant, but with the very distant you mean the one that help shape the spirals, the arcs.
So no, that is. No.
So there's another one. It's a
That is
fourth
much
star.
further. I mean, what I propose in the paper, which I wrote on the central compact dust cloud, was this was a triple system to begin with on the main sequence, and there is the EZK, whatever mechanism which makes the system unstable during the AGB phase, late main sequence, much later phase, and then the more, so the central binding which tightens up, and the third star moves up much further away. So that might be the explanation of, you know, what might have happened. So
One more question?
It's very good you present the barrel shape because this is a generic outcome of a jet interaction with a spherical shell. We see it also in some supernova remnants, and Muhammad Akashi here did simulations. But I said something about the triple. If you have triple strong interaction, usually you don't have two axis symmetry. You have departure, what we call MESI, planetary nebulae. So I didn't have time to look into the details, but if you have really some departure from axis symmetry, it might be really a triple merger maybe. So now we see only two. But there are ways for two stars in a binary system to change the direction of the jet. Imagine the companion comes close to the AGB socket. The AGB socket pulls it, and you have, it has huge convective cells. So it might be that one convective cell comes out and you have a short collision phase where the convective cell is imparting angular momentum in another direction. I did the calculation, and you can get quite jets that come in different directions in a binary system because of the very violent convection of the AGB star. This must be put into simulation eventually because it gives you jets in different directions.
Yeah, that's good to know.
And Joel, the equatorial material you see might be a binary ejection, but can be also that the lobes compress the material. Look at the simulations of Muhammad Akashi 10 years ago, 2015. You see that the two lobes can compress the equatorial outflow with many spikes that you see in 40. Really, you see many spikes, exactly what you get in simulation without equatorial outflow to begin with.
Well, let's thank our speaker again.
Okay, so now we move on to the posters, and we have a couple of substitute presenters. I think Joel started the trend here. So first, Maria Kopachini. Kopsaheli. It will present Sophia Theodossiou's talk on investigating the knots in the Balmer-dominated LMC supernova remnants. So we had a good lead in there on supernova remnants. And now here I will, it looks like it's a supernova remnant in the LMC.
Thank you. So, hi again. So yes, Sophia is a bachelor student. This is her thesis that she did at National Observatory of Athens with the ISM group. And it's about this LMC supernova remnant. So for this study, we used news data of this remnant, and we focused on the nodes of what that are actually dense circumstellar material released during the explosion of the mass loss episodes of the progenitor star. So in this study, we detect for the first time some emissions from these nodes, and also some iron structures that are probably related to the reverse shock. We also find that the oxygen emission comes from a region out of the front shock, which has undergone photonization and excitation from shock accelerated particles. Also, we use some emission line ratios in order to estimate density and temperature, and we put the nodes in diagrams of diagnostics, and we find that the most dominant mechanism of their emission is the shock excitation. We also here, the nodes actually show how the observational SNR region has to extend in order to take into account also LMC circumstellar material. And these dimensions are traditional diagnostics of supernova remnants. And finally, we find a linear relation between iron and nickel because of due to dust grain origin. And we find we see that there is a shift, like a downshift, compared to galactic nodes, and this is because of LMC's lower metallicity. Thank you.
So now, Stavros Akras will present for Lydia Constantinou, timeline of knowledge about low ionization structures in planetary nebulae.
Thank you. Good morning, everyone. So, yeah, I know it's quite difficult. It's in a portrait. It was difficult to switch in a landscape. So I have nearly 10 years working on clamps and low ionization structures. So I decided not give a poster working on emission lines, electron temperature density. So I decided to gather all the papers that I have read. Sorry if I have missed some paper. It's a timeline. Okay. Can we scroll up a bit? Okay. Sorry. It is not easy for so I start, I think it's 1987 with a work by Balik and colleagues with a telescope 2 meters, 4 meters, regular long slit work. Then we have more works with optical data mainly. Then in 98, we start having some models by Melema. A lot of works with groups working on helix, the cometary nodes, the non-cometary nodes going well. Then we have some CO emissions start coming in the play in 2002, as you can see. We have the HST images. So until down to 2026, 25, with the work by Lydia and Konstantinos. All of these are for nearly 45 papers. So I think it's a nice time view for the work that have been done on these cometary structures. Thank you.
And next we have a poster by Daniela Barria on the influence of a central star on ionization trends in planetary nebulae.
Good morning, everyone. My name is Daniela Barria. I'm from Universidad Central de Chile, and I'm going to present still work in progress with one of my students. And basically, we are creating extended diagnostic diagrams. Historically, diagnostic diagrams such as H alpha 2 and 2 to H alpha 2H2 has been used to discriminate between photoionized planetary nebula from shocked nebula like supernova or H2 regions. But all these previous studies has been done using the gaseous, the nebula has a total, or measuring the emissivity of the nebula has a total. So what we did here is just we try to describe the diagnostic diagrams and the emissivity tendency, but now considering a sample of 13 planetary nebula, including all the brightness surface of the nebula, but considering the different regions along each of these nebula. So basically, we, according to theoretical models, we expect for some kind of ionization tendency, especially on these low ionization ions like SN2 and S2. And this is an outside to inside ionization tendency. Okay, so you can see here that this is just basically the emission from the outer part of the nebula, and this is from the inner part of the nebula. So in each of them, we observe this ionization tendency, and we were at some point astonished when we found that this tendency is different for different planetary nebula. So actually, we wonder now if there is some influence of the central star parameters into this ionization tendency for this planetary nebula. And what we did is just we collect from literature several central star and nebular parameters, and then we compare them with the slopes of this main ionization tendency. And this is still a preliminary result, but here you can see the effective temperature of the central star in function of the slope of the ionization tendency. And as far as we can see here, it seems to be that as higher the slope of the ionization tendency correspond to higher central star temperatures. This still is a work in progress, as I mentioned before. And we also find that maybe the expansion velocity of the nebula can be also correlated to the slope of the ionization tendency. So, sorry, I forgot to mention that this is a work with one of my students, Chiara Angel, in Chile. Thank you very much.
Okay, now we come to the last poster, and now we make a complete cycle, returning to TC1. So you could say we have a closed carbon shell here. And Jan,
Right, thanks. So I just want to add on to the brilliant presentations by Morgan Giese and Simon van Scholenberg. So TC1 is the ideal source to study fullerenes for two reasons. Number one, if you look at the infrared spectra that we have, they're really clean emission features due to C60, no contamination bypass whatsoever. And second, it's spatially resolved. We can actually study the structure and how things change and connect that to the physical conditions in this object. And so here's a Muse image that we have. This is H alpha. Of course, we have an entire IFU cube. This is work done by Jeremy Walsh and Ana Monreal Ibero. And so if we combine our Muse images with the JMST data that we have, we see, as Morgan pointed